Hello students, today we are going to start our first unit and then the subject we are going to discuss is Automata and Compiler Design. So before going to start our subject, we would like to know some prerequisites. That means what are the basic knowledge I need to understand about this subject. So we all know the machine is called as computing device. That means any device that is capable of receiving information and processing it and produce output. These things are called as computing devices. So in order to program a computing device or in order to make it think like a human being, that we are calling it as human intelligence or machine intelligence. So these concepts resolves around a thing called as automation. So the thing that gives the seed to the automations are called as Turing machines, which is invented by Alan Turing, and he discovered it during the period of Second World War. So before going to start our topic officially, I would like to tell you a small story which enables or creates the ideology to create an automata machine. So during the World War, the Germans used a machine to encrypt their value. The machine is called as Enigma. So with the help of Enigma, they are going to send the message and they are going to decode it the same code. So to encrypt and decrypt the message, we have a setting called as Enigma setting, and over the Enigma setting, the possibilities are 15 lakh crores possibilities for each time they can encrypt and decrypt the message. So, a set of scientists or mathematicians group is formed by the United Nations and they want to decode the thing. So, during that period, to solve a thing or decode a code which is generated by a machine, the scientists come up with the idea they need to develop a machine. So that's how the Bombay or Turing machine is invented. After that, it led to the modern innovations of computers. So I hope you people got the point. So let us continue. Obviously, begin our first topic called as finite automata. In the context of computer science and formal languages, here the formal languages refers the languages that are used to give instructions to the computers. Those we are going to call it as formal languages at the low levels. Okay, we are having an alphabet. So alphabet in the finite automata represents a set of symbols. So we will discuss in the next slide what is the alphabet in a elaborated way, and a string of sequence of symbols. So alphabet is going to have set of symbols, and with the help of alphabet I am going to create string and a language, a set of strings over an alphabet. The possible number of strings that we can form over an alphabet is called as language, and a grammar is a set of rules generating the valid strings of that language. These concepts are foundation to understanding how to define and manipulate formal system, from programming languages to theoretical models of computation. So in this basic and our introduction, we have come up with three or four keywords. One is a alphabet, second one is a string, third one is a language, and fourth one is a grammar. So in this session, we are going to elaborately discuss about all these four things. After that, we move to what is actually a finite machine. That means finite state machine, and what are the types of machine I am having. That is how this session is going to be. So, first one, alphabets. The definition of an alphabet is an alphabet is formally defined as a finite set of symbols, typically denoted by a Greek letter sigma. So, that letter we are going to represent, or the symbol that we are going to represent alphabet in finite automata and theory is sigma, and it is established by the Greek letter. And what it's going to have is set of symbols, finite set of symbols. That means alphabet is not infinite, it must have only finite set of values. And what's my symbol then? These symbols can be anything. So that symbol can be a letter, a digit, a punctuation mark, or any other distinguishable character. So each and every character is, we are going to call it a symbol. For the example they have given, alphabets of 0 comma 1 is a binary alphabet. Alphabet of a comma b comma c to z represent set of lowercase English alphabets, and then the third example says plus minus star, and then division represents set of arithmetic operators. So I hope you people now got it. Whatever that comes within the curly braces over the sigma, we are going to write as alphabets, and each symbol is represented by unique values, and those values can be formed over anything digits, alphabets and digits. We can use special symbols also. Next one is strings. Strings are sequence symbols drawn from the specific alphabet. For example, 0101 is a string over the binary alphabet 0, 0. So understand this, students. We have alphabet called as 0, 1. The possible number of combination that we can make over with the alphabets are called as strings. In the example, they have formed 01 and 01. String is a finite sequence of symbols chosen from the given alphabet. It is essentially a word or a sequence of characters, and it's fundamentally concept understanding formal languages and computational models. And we have also a string which is null value. That means empty string is also called as epsilons or lambda. We are going to denote it by the symbol. In the finite sequence, a string is a sequence of symbol that has definite belonging to and end. Meaning, if the it is finite in length. For the example, if alphabet equal to a comma b, then a b, b are all strings. Length of the string is the number of symbols it contains. For example, AAB has a 3 length symbol. Then by understanding these two, the next thing we have to understand is what is a language. Language L. In automata theory, a language is defined as set of strings or sequence of symbols over a given alphabet. So whatever the concept of strings can be put together within a curly braces, then we are going to call it as a language. So how to form a language? For that we have to call some protection rules which is defined by my grammar. So while a grammar is set of rules generating or recognizing these things, a language can also be recognized by an automata, an abstract machine that process input strings and determine if it belongs to the language. So these languages are validated by a machine, and that machine is, for example, right now we are going to discuss about regular expressions. A language is said to be regular expression if it is attacked, if it is processed by a finite state machine, either NFA or DFA. So given examples. Example 1, a finite non-empty set of symbols. For example, a sigma equal to 0, 1 is the binary alphabet. String, a finite sequence of symbols from the alphabet. For example, 101 is the string over the binary alphabet. Language L, a set of strings over a given alphabet. A language can be a finite or infinite. So this is the important thing. Alphabet and string must be in finite state, but a language can be either in finite or infinite state. Example, if the given alphabet is a comma b, the language could be all strings that begin with a. Then we have to put the possibilities a b, a b. Likewise, it goes on. It is an infinity language. Then, what is a grammar? A formal set of rules used to generate and manipulate strings is called as protection rules. With these specific symbols and transition, we can put into a symbols and sequence of symbols. The formal definition of a grammar is often a tuple of 4 b, sigma, r and s, whereas v is a finite set of variables or non-terminal symbols. These variables or non-terminal symbols are placeholders which will be replaced by again a terminal symbol. The sigma is a finite set of terminal symbols. So whatever symbol comes within the sigma are called as the my terminal symbols. Then R is a finite set of protection rules that describes how to create a valid string. So on a particular language, by following the protection strings only, we are going to display the language. And S is the start symbol or special symbol to start the grammar. Components, terminal symbol that appears actually strings of the language. Non-terminals are the variables, symbols that are used to intermediate steps of the grammar and deviations but do not appear in the final stage. And production rules, rules that are described non-terminals can be replaced by non-terminals or terminals. A start symbol, a designed non-terminal from which the generation process begins. So consider this example. The grammar to generate a language of strings from A, N, B, N, meaning A replaced by N times followed by B. Alphabet given is A comma B and the starting production symbol terminal symbol is S, and the production rules is S tends to A capital S small b. Rule 1, generating number of A's and number of B's, and S tends to epsilon or lambda, rule to generate the empty string epsilon or the base case A or B. From the start symbol, S tends to A, S, B. Apply rule 1, then S tends to small a, capital S, B, and then small b. Then the third step, the symbol will be A, S, B, B. Again, we are going to replace this segment S with the second production rule, epsilon. So, A, epsilon, B, B. By removing the epsilon, we get the final answer as A, B, B. This is the basic language represented by this grammar. This language is generated number of A's followed by same number of B's. So the overall language will be like epsilon AB, AABB, AAABB, and it goes on. It is a finite file. And here comes the finite automata. Finite automata are abstract machines used to recognize patterns in input sequence, forming the basic understanding of regular language in computer science. Consists the state transition and input symbol, processing each symbol step by step. If the machine ends in accepting state after processing the input, then it is accepted, otherwise it is rejected. Finite automata comes in DFA and NFA. DFA in the sense deterministic finite automata, NFA in the sense non-deterministic finite automata. So as the name suggests, deterministic in the sense is going to end with a finite number of states, whereas in non-deterministic it's not going to end with a finite number of steps. They are widely used in text processing, compiler design, and network protocols. So this is the sample examples. So each symbol is given to the automata, and it is going to tell the result whether it is accepted or not. Acceptance will be in the output form. So the features and formal definition of finite automata. Features are input, set of symbols, outputs, accepted or rejected state, states of automata or intermediate state, state relation, the transition between the states, output relation. Based on the final state, the output decision is made. The formal definition of finite automata is a 5-tuple Q, where Q is a finite set of states. Sigma, we have known what is sigma, and Q naught is the initial state. F represents the final state, and the symbol transition function, and the transition function we are going to use the symbol called as delta. So the types of finite automata, deterministic finite automata, and then non-deterministic finite automata we are going to discuss one by one. DFA is also represented as a tuple of 5 as we discussed in the finite automata, and DFA, for each input symbol the machine translates one and only one state. That means for a particular state the given input is 0 and it's going to transfer to either only one state, not going to two states. For a given input a machine can do only one transition and does not allow null transition. What means in DFA we cannot do epsilon transition, meaning every state must have a transition defined for given input. So the 5 tuple are the same as the finite automata Q, sigma, Q naught, F, and then transition function. Whereas the transition function of DFA is Q into sigma will produce another Q. That means a state into input symbol will produce another state. So given example, given alphabet is A comma B and the states are Q naught and Q1, final state is Q1. We have to construct a DFA that accepts all strings ending with A. Okay. For the example, the initial state is represented by Q naught, and whenever I receive A, it will go to the final state Q1. After reaching the final state, whatever comes, either A or B, no problem. I have to here the thing is ends with A. Whenever after reaching the final state A comes, it's going to stay in the final state. Otherwise, it will come back to B, and again whenever A comes, it will go to Q1. So this is the DFA for that, and for the DFA diagram, we have to construct the symbols. That means state transition table. The second one is non-deterministic finite automata. So the major difference between NFA and DFA is in DFA we don't have null transition, and for a particular input we can move to only one state. But here look at the diagram that we have shown in the display. For a single input A, the transition from Q naught will go to two values. Q naught can stays itself in Q naught, and also it can goes to Q1. So this represents the difference between NFA and finite DFA. The same example we are going to accept the strings by using NFA, which is ends with A. So the machine can stay in A and B whenever the transition begins, but the final value is A, it can goes to Q1, otherwise it will be in Q0 only. Here look at the transition table. For Q 0 on A, it can goes to Q 0 and also Q1, and for Q 0 on B, it can goes to Q 0. By just understand the value for Q1. For Q1, we are not going to go where anywhere, because after reaching the final state, the machine has to stay itself. So we are representing the null values by 5. That means in DFA we cannot represent the null values by 5, whereas in NFA the null values can be represented as 5. So we are going to do a quick comparison between DFA and NFA. Although NFA appears more flexible, they do not have more computational power than DFA. Every NFA can be converted into an equivalent DFA, although the resulting DFA may have more states. DFA single transition for each input, no null value moves, whereas in NFA multiple transition for each input and null value is allowed. Power, both the DFA and NFA recognize the same set of regular languages. Conclusion, finite automata, whether deterministic or non-deterministic, both are powerful tools in pattern recognition and regular language processing. They form the backbone of many computational processes, especially in text analysis and compiler designs. Understanding the nuance of the both helps in optimizing various algorithms in computer science. Thank you, students. I hope this session is very useful for you. Thank you.